Hi, I'm Dr. Jim Zoval, a professor of chemistry at Saddleback College. You're about to watch one of my video lectures. If you like this lecture, you can get the entire Allied Health General Organic and Biochemistry course from the website address you see on the screen right now. Be sure to type the underscore between VOD and pages in this address. Enjoy the video. Here's some common errors you want to avoid when you're balancing equations. You don't want to change the product or reactant to another substance. For instance, if I'm trying to balance this, I have 2 nitrogens, 2 oxygens, 2 nitrogens, 1 oxygen. I don't do, okay, there, it's balanced. Right? I don't change the product. That's at some pressure and temperature, that may indeed occur, but that's not what we're talking about here. We're talking about this reaction. So don't do that. What you might be tempted to do on that one is say, okay, I need another oxygen, just put plus O. Well, if that's what happened when you mix nitrogen and oxygen, that you got N2O and some oxygen atoms, which are highly unstable because the octet rule is not satisfied, right? Then that would be right. But that's not what happens. This is what happens. So don't do that. If you've put those coefficients up there and at the end you get it balanced, and you notice that those coefficients are multiples. For example, all these are multiples of 2. When it's 4, 2, and 4. We don't say, this is just the ratio that things react. It reacts, 4 of those would react with 2 of these to produce 4 of those. What ratio would we use? 2 to 1 to 2, right? We saw that, remember when you did the crisscross method for writing the formula of ionic compounds? We always use the lowest ratio. Same thing here. We wouldn't say 4 to 2 to 4. We'd say 2 to 1 to 2. So don't do those things. Now that we could take a reaction and balance it, know the ratio that the reactants react with one another and the ratio of products that gets made, we could start to do some calculations. If we're going to do a reaction, say we're given a certain so many grams of reactants, how many grams of product can we get? We could start to do those now. And I want to show you how, and that's what we'll work on for the rest of the lecture today. This process of doing this is called stoichiometry. Just like we saw the cheese sandwich example, building an airplane is kind of analogous to a chemical reaction. The product of the reaction is an airplane, right? What are the reactants? All the parts, right? The wings, the engines, the tails, the windows right here. And if you want to figure out how many planes you could make, you need to know how many parts you have. Same thing with chemical reactions. Once I run out of a part, let's say I run out of the left wing, that's it, I'm done making planes for the day until I get some more left wings. Same thing with chemical reactions. So stoichiometry deals with how much. Here's a pronunciation thing. Stoichiometry. When I first met my wife, she was getting coffee somewhere and she asked me how many creams and sugars. So I said, well, I use a stoichiometry of 2 creams and 2 sugars. She looked at me like I had 3 heads because she didn't have a chemistry class. I'm quite used to that look by now. I get it all the time, but that was one of the first times. But once I explained to her what stoichiometry was, she got a kick out of it, and she uses it all the time. Yeah. Anyway, she married me anyway. I guess it was a yellow flag, not a red flag. If I would have started screaming about too much sugar, then she probably would have said, you know, it was nice meeting you. Maybe I'll call you. Have a good evening. Take care. Goodbye. Adios. Stoichiometry deals with calculations about the masses of reactants and products involved in a chemical reaction. Say this is a pile of reactants and the chemical reaction happens and it makes some products. You might get a certain amount of product. You might have some reactants left over. Stoichiometry allows us to calculate these types of things. What we need to start with is the balanced chemical equation, and that's what we just learned. If you start with the balanced chemical equation, we could predict which reactants will run out, how much product we'll need. We're going to do some of those, but I want to go back to something you're more familiar with, food. Let's do a stoichiometry problem. So you want to make as many cheese sandwiches as you can. If you have 20 slices of bread, how many slices of cheese would you need? Right. You guys immediately knew that, right? The same thing's going to happen with chemical reactions, and it's going to be that easy. But you guys really did this stoichiometry calculation in your head. You started with the balanced equation, right? There it is. There's the chemical equation that you had in your head. And you did a calculation. These are just unit conversion problems. You converted from what to what? Yeah, you converted from slices of bread to slices of cheese, right? It's a unit conversion. So you, just like any unit conversion, you write down what you start with, then you multiply it by the conversion factor. There's the conversion. If you want to convert from bread to cheese, you need the relationship between bread and cheese, just like you would if you wanted to convert from inches to centimeters, you'd need the relationship from inches to centimeters. This is the conversion factor. Now we need numbers here. Where do you think we get these numbers? From the chemical equation. Watch the animation. And you guys knew this. You guys knew that for every 2 slices of bread, you need 1 cheese slice. I'm trying to convince you guys did this calculation in your head when you all said 10 slices of cheese a moment ago. So we converted from slices of bread to slices of cheese. Unit conversion, do the units. Slices of bread cancel, and you end up with slices of cheese. And you guys yelled out 10 slices of cheese right away. You did that in your head. And if we did it this way, you guys, that's the way we do our unit conversion problems, right? You did that so fast you don't even realize you did it. It's because it's familiar to you. It's something that you're quite familiar with. When we start doing chemical reactions, it's the same thing. Don't make it any more difficult than this. It's the exact same thing. Someone was on a cruise ship, they got a piece of bread and they saw something in here. Do you guys see anything? Oh, yeah. Depending on your cultural background, people see different things. A woman. Who?
Kind of looks like a photo of
Marlene Dietrich, Mary. Someone else in another class said Madonna. Just kidding. All right. I guess the story is that they froze this and it ended up selling online, I think, for $1,000 or $10,000 or something.
It's a piece of bread?
It's a piece of bread with an image.
It's art.
That's not coincidence.
But that's how it came.
Huh?
How it came.
Yeah, they took it off the grill and that's... Okay, I'm joking. I think it's just a piece of bread too. I wouldn't spend more than, I don't know, on a cruise ship you get it for free. You only have to spend. All right, let's do the same type of calculation for a chemical reaction. Carbon monoxide reacts with oxygen gas to form CO2. So I balanced it for you. We have the balanced equation there. We could answer some pretty basic questions. I'm going to ask you some things. You might think that if you think it's too easy, it's not. You got it right. It's just really simple, right? So we get asked this. How many CO2 molecules are produced from 2 molecules of carbon monoxide? It's not a trick question. 2, yeah. That's what these numbers tell us. How many O2 molecules are needed to produce 2 molecules of carbon dioxide? 1. And you don't see a number there, it's a 1. Right? One more. How many carbon monoxide molecules are needed to react with 1 molecule of O2? 2. It's 2 to 1, right? We could think of those as the ratio that the molecules react, or if it's an ionic compound, the formula units that react. Or we could think of it as the number of moles that react also. Right? Because we usually we don't do reactions with just 1, 2 molecules. We have millions of them in a sample and they react. So we could think of these numbers as either the ratio 2 to 1 to 2. 2 molecules react with 1 molecule to produce 2 molecules, or 2 moles of that substance react with 1 mole of this substance to produce 2 moles of that substance. How many moles of carbon dioxide are produced from 2 moles of carbon monoxide? Yeah, it's the same numbers, right? Just think of this as molecules or moles. How many moles of O2 are needed to produce 2 moles of CO2? 1. These are just the same questions. The point is you could answer these as either molecules or moles of the substance. How many moles of carbon monoxide are needed to react with 1 mole of O2? 2, right? Let's think of a certain amount of reactants we start with. So let's say we're going to start with 6 moles of carbon monoxide. How many moles of CO2 will be made if all the carbon monoxide is used up? We'll assume we have an unlimited supply of O2. Now, this is the same kind of thing as the cheese sandwich. We're going to do a unit conversion. We're going to convert from moles of carbon monoxide to moles of carbon dioxide. So with our unit conversions, we'll write down what we start with, just like we did right when we did the bread, 20 slices of bread. Here we're going to start with 6 moles of carbon monoxide, and we want to know how many moles of CO2 we're going to make, so we're going to convert from moles of carbon monoxide to moles of carbon dioxide. So we need the conversion factor. This is the relationship between carbon monoxide and CO2. We haven't put the numbers in. Where do we get these numbers? From the balanced equation, right? And so I'll get them, watch the animation. 2 moles of carbon monoxide will produce 2 moles of CO2. Moles of carbon monoxide cancel, and we calculate how many moles of CO2 will be produced. And it should make sense since it's for every 2 of these, you get 2 of those. It's like a 1-to-1 ratio, right? 6.0 moles of carbon dioxide would be produced from 6.0 moles of carbon monoxide, assuming you have an unlimited supply of O2. We could do them this way if we want. Just a unit conversion. Another mole problem. Okay. So let's convert. We want how many moles of O2 will be needed to react with 6 moles of carbon monoxide. So we're going to convert now from moles of carbon monoxide to moles of O2. So we write down what we're starting with. We put the conversion factor in here. We get these numbers, the relationship between carbon monoxide and O2 from the balanced equation. Notice when you don't see a number there, I just made it appear there's a 1. So 2 moles of carbon monoxide react with 1 mole of O2. Moles of CO2 cancel, and we get 3 moles of O2. 6 moles of carbon monoxide require 3 moles of O2. Same way. One more. Why don't you guys do this one? How many moles of carbon monoxide are needed to produce 7.50 moles of CO2? Assume you have an unlimited supply of O2. If you're watching the video, click pause and work on this problem. Let's take a look at the solution. Here we want to convert from moles of carbon dioxide to moles of carbon monoxide. So we start with what we're given. We're going to convert now from moles of carbon dioxide to moles of carbon monoxide. We're going to get these numbers from the balanced equation. Notice for every 2 moles of carbon monoxide, we produce 2 moles of CO2. Moles of CO2 cancel, and we get our answer. They react 2 to 2, so it's the same number. It's just kind of like the sandwiches. If you do it with these lines, your equation would look like this. Okay. Hi, I'm Dr. Jim Zoval. If you like this video and you'd like to get the entire course or just some of the chapters on video, I have the entire course in video lectures at the website you see on the screen right now. They're available on demand. The period of the rental is for a full year, so you'll have this video through the entire course. You could watch it as many times as you want, whenever you want. Happy studies.